So today I will start to design of beams and columns. Let's start with first with beams. Just to remind you what we learned previously, we can get the applied load on a beam, W ultimate, and we can figure out the shear force diagram of this beam and the bending moment diagram for this beam. So we can figure out V ultimate and M ultimate from loading. If you have dead load, live load, and each beam is supporting from center line to center line, we can figure out these loads and we can draw shear force diagram to get the maximum value, which we call V ultimate, and the bending moment diagram, the maximum value can be called M ultimate. Today, we will start to design. Let's start first with something very interesting. As a civil engineer, you have to remember this information. And this information also is required for your professional engineer exam. What is the meaning of plastic moment, which called MP? Let me explain it step by step. If you have a beam with concentrated load, this concentrated load will make moment. This value of moment with sigma equal MC over I can construct this stress diagram. We have stress compression at the top, tension at the bottom. I can draw this stress diagram. First stage, this applied load is very small. So the stress, the maximum stress in steel, less than yielding stress. If the applied load increased a little bit, the bending moment diagram will increase. So if the moment increase, sigma will increase. So the stress or the maximum stress at the top or at the bottom equal yielding. Just at the top and the bottom. If the applied load increased more and more, so the bending moment diagram will increase more and more. So the stress will not increase because the maximum is F yield. But part of the cross section will be yielded. Remember the previous situation? The extreme fibers only yielded. If the load is increased, we have more yielded part of the cross section. Okay, can you imagine if we increase this load more and more and more until the whole cross section is yielded? At this time, the bending moment diagram at this exactly time, the maximum or the bending moment diagram can be called plastic moment. Plastic moment means the whole cross section is yielded. And remember, we have part of the cross section under compression and the other part under tension. In between, we have something called neutral axis. I'm sorry. In this case, this neutral axis is special. This neutral axis can be called plastic neutral axis. So just to give you a hint, this part is very important. Believe me, if you have a steel cross section and you are looking for plastic moment, M plastic. So that means Here is the cross section. That means we have one part of the cross section is under compression. And the stress on this part is yielding. And the stress on the other part of the cross section under tension. And this part is yielded. The transition between tension and compression, we have a line here. This line can be called plastic neutral axis. So this part under compression yielded. This part under tension yielded. And this is the stress distribution at plastic moment. So plastic moment means the whole cross section is yielded, not one part or two parts or part of the cross section. No, the whole cross section is yielded. One side of the cross section under compression, if yield, and the other side of the cross section under tension also yielded. The transition between the two sides called plastic neutral axis. Any question? Any question? If your cross section is symmetric, this part exactly equal to this part, make sure and believe me, the plastic neutral axis will be at the middle point. If not, so if the cross section is not symmetry, then the plastic neutral axis will be somewhere. I don't know where exactly, but it will be in between. Any questions so far? So did you understand what is the meaning of plastic moment? Plastic moment is a moment, but called plastic because the whole cross section of the steel member is yielded. And I told you we have different level of yielding. If you have very small load, a little bit bigger, a little bit bigger and bigger, and the maximum one to cause plastic moment. Yes, okay, let me explain it in more details. If you go back for the previous semester, I told you if you draw a stress strain curve between the relationship between stress and strain for steel, you can find it like this. At this location, we have yielding. So if you reach yielding, that's fine. We don't have issue, but we don't like plastic because if you go after yielding, you can expect permanent deformation. But at this location, you still very close to the elastic behavior. You know, we don't like to go beyond this point because if you go beyond yielding, you can expect strain hardening behavior and you can expect permanent deformation. Okay. We have example here. This example is one problem in one of the professional engineer exam. We have singly symmetric eye-shaped. Singly symmetric means symmetric about one axis. The other axis is not symmetry. Made from steel A36. From this information, I can say if yield for this steel equal 36 KSI. Okay, so after your graduation, you have to be familiar with this information. A36 means we have a steel with yielding stress equal 36 KSI. What is the plastic moment of this cross section? Everything is given about this cross section. like the top flange width, this flange has a width 12 inch. Bottom flange width, this flange is 10 inch. Top flange thickness, this flange 1.5 inch. Bottom flange thickness, this thickness 2 inch. Web thickness 3/4, this thickness 3/4 inch. The overall depth, this total depth 22 inch. This is the reason why the problem said singly symmetric, because this cross section is symmetry about this vertical axis only. So it's single symmetry, but not symmetric about the horizontal axis. We need to figure out what is the plastic moment. Let me explain it here. Here is the top flange. Here is the web. Here is the bottom flange. Anybody can tell me what is the meaning of reaching plastic moment? Means we have one part of the cross section, which is the top, will be under compression, and the stress will be F yield. Compression. The lower part of the cross section will be under tension, and the stress will be yielding. The transition between tension and compression, we have something here called plastic neutral axis. Do you know where is the plastic neutral axis? Do you know where? Anybody knows where is the plastic neutral axis? Do you know? Any answer? Anybody knows where is the plastic neutral axis? No. Okay. Let me explain it one more time. If you have cross section like this, not symmetry, and from engineering mechanics, we learn it. We can assume here reference, we can assume here reference, and this part has a centroid, this part has a centroid, this part has a centroid, and we can figure out where is the centroid for the whole cross section. For example, it will be here. Here is the x-axis, here is the y-axis, here is the centroid of the whole cross section. We can figure out this value by summation area y divide summation area, and x bar equals summation area x divide summation area. We learned all of this stuff in engineering mechanics. That's right? I need answer, yes or no. That's right? That's right? We learned all of this stuff. We can figure out where is the centroid of any cross section by using this technique. If you remember one more thing, we can set up a table. Here is the number of parts, part number 1, part number 2, part number 3. Here is the area, here is the x bar, here is the area times x. We can get the summation, and we can figure out this value to figure out the centroid. Yes or no? That's right? Unfortunately, this centroid and this horizontal line is called elastic neutral axis. Elastic neutral axis. This centroid and this neutral axis must be called elastic neutral axis. But here we are talking about something different. It's very important to understand this concept. Very important. Right now, we are talking about something different, something called plastic neutral axis, which is not coincide with this one. I don't know where it is. Okay, let's do it step by step. If we assume this height is y, can you tell me what is the value of this height? Any answer? No, it's not 22, 18.5. That's right. 18.5 minus y, because the whole depth is 22. So I believe the depth between this surface and this surface will be 18.5 if you subtract 1.5 and 2. So if you assume this one is y, this one will be 18.5 minus y. This top flange will have compression C1. This little part of the web will have compression C2. This bottom flange of the cross section has a tension T1. This little part of the web will be under tension T2. Go ahead and figure out C1 equal the area of this flange time this stress yielding. So we have 12 times 1.5 times 36. C2, the area of this web, which is 3/4 times y, the stress F yield 36. So what is the value? 12 times 1.5 times 36, 648. Keep the value here, 27 y. Keep walking. The tension at the bottom equal area of this flange times stress in this flange, which is yielding. So we have 10 times 2 times 36. What is the tension in this part of the web? The area is 18.5 minus y times thickness 3/4 time F yield 36. These values 720. Okay. This one will be 499.5 minus 27y. We learned from concrete design, if you apply summation f of x equals 0, we must have C1 plus C2 equal T1 plus T2. The compression on this side of the cross section must equal the tension on this side of the cross section. Okay, go ahead and put your numbers. We have 648 plus 27y equal T1 720 plus 499.5 minus 27y. I think the only unknown in this equation is y. I can figure it out. What is the value of y? 720 plus 499.5 minus 648 divide 27 two times. 10.6. So this y equal 10.6. So the depth of the neutral axis from the top will be, if you add 1.5, this one will be 12.1 inch. So the location of the plastic neutral axis will be at a distance from the top 12.1 inch. So did you understand how can we figure out the location of the plastic neutral axis? Did you remember how can we locate the elastic neutral axis? It's a big difference. And this problem is very important if you are planning to professional engineer exam. You have to understand what is the difference between elastic, which is piece of cake, for first step. Where is the centroid? At this centroid, you have neutral axis. This neutral axis is called elastic. But if you would like to figure out where is the plastic neutral axis, plastic means the upper part of the cross section is under compression and yielded. The lower part of the cross section is under tension and yielded. The compression on the upper part equal the tension on the lower part. You will ask me, hey, why you divided the compression to two parts, C1 and C2? Because we have two different areas. The area of flange has area, and the area of the web. So we have C1 and C2. And the same also, we have a part of the web and the part of the flange. So we have T1 and T2. Summation f of x equals 0. So C1 plus C2 it must equal T1 plus T2. Set up this equation. You have only one unknown, which is y. I can figure out the location of the plastic neutral axis. If you would like to get M plastic, go ahead and take moment around plastic neutral axis. I'm sorry. Yeah. Sit down here. Sit down here and take moment. What you mean? C1 time distance plus C2 time distance plus T1 time distance plus T2 time distance. Let's do it. C1 time distance plus C2 time distance plus T1 time distance plus T2 time distance. The final answer will be plastic moment. Anybody can tell me what is the distance between C1 at the centroid of the top flange? What is the distance between C1 and the plastic neutral axis? It will be 10.6 plus 0.75. This distance will be 11.35. What is the distance between C2, which is at the centroid of the web under compression, and plastic neutral axis will be half 10.6, which is 5.3. What is the distance between T1 at the centroid of the bottom flange and the plastic neutral axis? 18.5 minus 10.6 plus 1, 8.9. What is the distance between T2 at the centroid of this part of the web and the plastic neutral axis? It will be 3.95. The values of C1 and C2 and the T1 and the T2 are unknown, are known. After you got Y, I can figure out, C1 is known. C2, I can figure out what is the value of C2 because you know what is the value of Y. T1 is known, and this T2 can be known because Y is known right now. So once you put your number, I can get a final answer which called plastic moment. So one more time. If you have a problem, asking you where is the plastic neutral axis, or asking you about the plastic moment. It's very easy, but keep in your mind, we have a different technique used to locate where is the centroid. This centroid, based on these calculations, this neutral axis can be called elastic neutral axis. You are in the elastic region. But if you are in the plastic which is yielding, we have a different technique. The different technique, one part of the cross section under compression, the other part under tension, the transition between the two parts is called plastic neutral axis. You have to remember, any compression force on the top part must equal any tension force in the bottom part. So summation f of x equals 0. If you set up this equilibrium, I can figure out the unknown because I assume that the plastic neutral axis at distance y, so the remaining distance will be 18.5 minus y. I set up my equation. I found the value of y. Then to figure out the value of plastic moment, go ahead and take moment at plastic neutral axis. So any force time distance, any force time distance, any force time distance, any force time distance, set up your equation. You can figure out the plastic moment. Any question? This information is very important. Important for your exam and very important after your graduation. You have to understand what is the difference between elastic neutral axis and the plastic neutral axis. What is the meaning of plastic moment? Any question? This problem is one problem included in one of the textbook for professional engineer exam. Okay. Classification of cross section. Just to make sure you understand this part. Any cross section like W shape, this part of the cross section called flange. This part of the cross section called web. This part of the cross section called flange. To make sure we have a difference between the two flanges, this one called be top flange, this one called be bottom flange. Any question? We have three techniques or three categories for this cross section. Sometimes this cross section can be compact. We like it. We like our cross section to be compact. Sometimes it's non-compact. Sometimes it's slender. Guys, to make sure you understand what is the problem with steel cross section. The problem is, what do you think if we put a beam on another beam on this part? Do you expect some deformation on this part of the flange? Do you expect rotation or torsional of this beam? We don't like all of these issues with the steel cross section. So we would like to divide or to determine what is the classification. According to AISC, we have three classifications of any cross section. Your cross section can be compact. We like it. Your cross section can be called non-compact. We don't recommend it. Cylinder, we don't recommend to use cylinder cross section. Cylinder has big issue with buckling, with lateral torsion buckling, with all of these issues. Anyway, it's not our topic right now. How can I classify my cross section to be compact or non-compact or cylinder based on this table? We have a value called lambda. We have a value called lambda plastic. We have a value called lambda R. Lambda for the cross section, if you are talking about flange, let's start with the flange. Flange means this part or this part. By the way, the flange has something called B flange, which is the width, and T flange, which is the thickness. B flange, width, and T flange. If you divide B flange by 2 T flange, you can get lambda for this cross section. Lambda plastic or lambda P equal 0.38 square root E, Young's modulus of steel. Do you remember that? 29,000 KSI. I told you before, keep this number in your mind. Divide F yield based on the type of steel, I can get the value of lambda plastic. Lambda R, 1 square root E divide F yield. What is the relationship between lambda and the lambda P and the lambda RF? Lambda smaller than or equal lambda P, compact. Lambda between lambda plastic and the lambda R, non-compact. If lambda greater than lambda R, will be slender. Does that make sense? What you did with flange, you have to do it with web. H divide T web. By the way, this web has H and we have T web. H for the web only, T web the thickness. If you divide H by T web, you can get lambda. And you can get lambda plastic for web and the lambda R for web. And then make a comparison between lambda P, and lambda R based on this relation. Based on this relationship, I can figure out the compact, non-compact, and the cylinder. Make sure the category is based on the worst width to thickness ratio of the cross section. What you mean by the worst? For example, if you found this flange is compact, which is good. This web is compact, which is good. This bottom flange is non-compact. So what is the final conclusion about this cross section is non-compact? We are taking the worst case. As I told you, if you found this flange compact, if you found this web compact, if you found this flange non-compact, the whole cross section will be non-compact. For example, another example, if you have this cross section and you found this one is non-compact and you found this part is compact and you found this one is cylinder, what is the final conclusion about this cross section? Cylinder. We have 3 categories: cylinder, non-compact, compact. The category is based on the worst cross section. If the web is compact and the flange is non-compact, the shape is classified as non-compact. All sections in table are compact. What you mean by this one? If you have a table like this and you have cross section, without any calculation, this cross section will be compact. Believe me. Okay, we are talking about built up section. If you have this part connected to this part, connected to this part, and you create a cross section. What is the category of this cross section? Then we need to do calculation. But if you select a cross section from the table, believe me, this cross section will be compact. Let's do an example. But before doing the example, any question? If you have any question, let me know. Okay, we have this double symmetric eye section is shown below. Determine if the cross section is compact, non-compact, or cylinder. If yield equal 50 KSR. Do you think the top flange looks like the bottom flange? I think so. One of them will be enough. Let's start with the flange. If you have two different flanges, like this example, this flange is different than this one. You have to do for each one of them. Okay. Okay. So flange, B flange equal 12 inch. T flange equal 2 inch. So B flange divide 2 T flange, which is lambda. B flange divide 2 flange. How much? 12 divide 2 times 2 equal 3. So what is the value of lambda P? What is the value of lambda R? Lambda P 0.38 square root E divide F yield. Okay, 0.38 square root E 29,000 KSI. If yield is given 50, what is the value? 29,000 divide 50 square root times 0.38, 9.15. What is the value of lambda R? 1 square root E divide F yield. E 29,000 divide 50 square root equal 24. So what do you think? What do you think? I think lambda, which is 3, is smaller than lambda P, which is 9.15. So your category will be compact flange. Very easy. Let's start about web. H equal 48 from this surface to this surface. T web equal 0.5. So H divide T web equal 96, which is lambda. Can you tell me what is the value of lambda plastic or lambda P? 3.76 times square root of 29,000 divide 50. This value will be 90.6. This one will be 137. Lambda R, lambda P. So what do you think? Our value is 96. 96. Wow. So lambda is greater than lambda plastic and smaller than lambda R, because 96 between 90 and 137. So what do you think? Your web will be non-compact web. The final conclusion for this cross section, because we are not looking for compact or non-compact for each part. We are looking for compact or non-compact or cylinder for the whole cross section. What is your final conclusion? Non-compact cross section. Any question so far? So right now, we learned what is the meaning of plastic analysis, plastic moment, plastic neutral axis. How can we figure out where is the plastic neutral axis? What is the value of plastic moment? How can we figure out the classification of the cross-section of steel cross-section, compact, non-compact, or cylinder? And we have example. Any question so far? If you have any question, let me know. Okay. Do you know what is the meaning of lateral torsional buckling? Lateral torsional buckling. A beam is considered and restrained when its compression flange is free to displace laterally and rotate. Can you see here? Displace laterally and rotate. Which flange? Any flange? No. The compression flange. That when under compression, we have collapse here for this steel beam due to the effect of lateral torsional buckling. This beam is supported on this side and this side. We expect moment on this beam, so the top part will be under compression. The bottom part will be under tension. We don't have issue with tension in steel. Tension is good, but compression will cause if this flange is not supported. We expect lateral displacement and rotation of the steel beam. If you would like to understand this phenomenon correctly, let's start to watch this video. It's a good experiment. So guys, in this beam or this experiment, we have a steel beam supported from this side and supported from the other side, and we have concentrated load at the middle point or at the midpoint. So see what will happen. Okay, so I expect the top flange will be under compression and the bottom flange will be under tension. That makes sense for me. Can you see this diagram and this diagram? The first diagram represents the vertical displacement. We understand if this load is applied, the beam will deflect downward. And the second diagram represents horizontal displacement. What will happen for the top flange, which is under compression? Can you watch? Everybody, can you watch? Until this moment, we have vertical displacement around 10 millimeter. This beam deflected downward 10 millimeter. But for the horizontal displacement, it's almost zero. We don't have any horizontal, we don't have any lateral displacement. Can you watch more? Hey, can you watch what's going on? The top flange, which is under compression, started to deflect laterally. And the steel beam start to rotate. One more time. Can you see? One more time. If this happens, we cannot expect more load can be supported by the beam. The beam started to fail. This phenomenon called lateral torsional buckling. Lateral torsional buckling. This happens for the compression flange of any steel member. So how to overcome this problem? We can use bracing. Can you see this bracing? If you are watching any steel bridge, you can see we have cross bracing like this. So the top flange, which is under compression, is supported by this bracing to the bottom flange, and vice versa for this one with this one. So if the top flange started to move laterally in this direction or this direction, this bracing will prevent this phenomenon. Lateral torsion buckling can be prevented by bracing the beam against twisting at sufficiently close interval. These bracing are repeated at sufficient interval. Any question for this phenomena? It's very important to understand what is the meaning of lateral torsion buckling. We don't like this phenomenon with the steel members. We don't like it because if you expect what would support the flange to defend against. Thank you, Oliver, for your question. The answer is bracing. If you are watching any steel bridge around you, you will find this bracing, and this bracing will be repeated at equal interval. The distance between each bracing will determine if you have lateral torsion buckling or not. We don't like collapse due to lateral torsion buckling because lateral torsion buckling will make your member weak, cannot support the desired load. We learned a lot today, I think. Many concepts, starting from plastic analysis. Actually, we have an advanced course called Plastic Analysis of Steel Structure. It's more advanced for graduate students. And classification of cross-section and the phenomenon lateral torsion buckling and how can we prevent this issue. So if a beam remains stable up to its full plastic moment capacity, it's compact section. Failure will be by yielding. Instability, instability, we don't like this word. Instability. Could be overall beam instability for non-compact section or instability for local instability. What you mean by local? Okay, go ahead and start to watch this video. Local means very small part of the beam failed. Can you see here? Guys, can you see this part of the flange? It's local. The whole beam is good. Only this part of the flange, this called local failure. This happens if you have cylinder cross section. This is the reason I told you we like your cross section to be compact. We don't like to be slender. In between, non-compact, we like and dislike. So compact section, the whole cross section is working and the failure will be due to yielding in material. But if you have non-compact cross section or cylinder section, you have to expect instability. What is the difference between this instability and this instability? The first one, instability for the whole beam. The whole beam is unstable if you have non-compact section. But if you have cylinder section, the instability will be one part, single part, small part of the beam will be unstable, which is called local instability, like this video. This one is local instability. We don't like this because the whole beam is still good. Only this part is failed. We don't like this.